Probably whiteboard. Less messy. I'm sorry, Ryan. Whiteboard, please. Go ahead and sort of space yourselves out so the rest of the class can see you. This is the old Sesame Street little segment where they would put up the 4 pictures. We only have 3 pictures. One of these things is not like the others. We won't go into the one of these things just doesn't belong. That would be cruel. But if you take an eraser, well, any rectangular solid, that has 3 axes of symmetry. So there's one that goes right through this way, horizontally. And if you take a point on the eraser and go back through that line, there's another point that's equidistant on the other side, which is what we mean by a line of symmetry. There's another one that goes through it this way, and there's another one that goes through it lengthwise. So we have 3 axes of symmetry, which means that we can spin this thing 3 different ways. So you can spin it, if I want to spin it around this axis here, the one that's pointing out that way, I can just sit and spin it that way. You can spin it around the long axis, or you can spin it around this axis. So what we're going to do is we're going to give each individual their own axis. We'll start, Sarah gets to pick first. Which axis do you want?
I'm going to go with this one.
That one? All right. So she's going to spin hers around that one. And you need to, good spins, so people get a real chance to see it spin. And which one do you want, Ryan? You either get the long axis or this one.
I'm trying to.
You're going to do that? So you're going to do it around this axis?
Yeah.
Okay. So I guess you get the long axis.
This axis.
Yeah, okay. So go ahead and spin your erasers. Your job, as the rest of the class, is to identify which of these things is not like the others, and we're not talking about physical dexterity here. We're talking about the way the eraser just naturally spins. Well, make it spin, right?
I'm not that coordinated
Just go.
like you.
Just, yeah, well, years of practice. There you go, perfect, very nice. And real free spin.
Like this?
There you go, yeah. So, try and spin them, nice and high so we get multiple spins.
I'm sorry, I don't see the difference in those.
No, one of them is not like the others. Just keep it to yourself. We'll watch for just a minute. Actually, I guess when you decide you've seen one that's different, then raise your hand and we'll see where we are. Peer pressure is rippling across.
Everybody looks around, but
Eeny, meeny, miny, mo.
Good damn wore a white shirt.
Yes. Now we're not going to spend all day on this, so we will have to make a decision at some point. So I'll give you about 30 seconds here for the last few of you to come to some conclusion as to who's different. Where have we got everybody? I think we're there. All right, so thank you very much for our volunteers. Not in a pejorative way, but who was different? Who had the different spin? Sarah?
yeah.
How many vote for Sarah? That she had the different spinning eraser. I thought we just had some votes for her.
I was pointing at
Oh, you were pointing at him. So no one votes for Sarah. Okay. Any votes for Ryan?
That's all right.
A couple of votes for Ryan. So I take it everyone else votes.
Yeah,
All right.
that's right.
So let me. So we're going to go back. Which one did you have, Keith? You had the long axis, right? So we had the long axis, which is that spin. And then you're saying that that in some way is fundamentally different from that spin.
It's odder than it looks.
It is. Especially with these ultralight erasers.
Yeah,
I'm used to something with some bulk to it. And this one. What's different, what would you say is different about the long axis spin, Stephen?
That it tumbles. It doesn't actually. Or I'm talking about the one that Sarah did. Sorry.
Okay.
That's the other long axis.
Didn't think anyone voted for Sarah.
I did.
You did?
Yeah.
Oh, I'm sorry, I missed your vote.
Sorry. I was alone.
It's like me when I write in candidates. Never shows up anywhere. Nobody registers my vote. Those of you who voted for Keith, what do you say is different? What did you see different?
The rotation of spin was a lot faster than the others.
Okay. So I can get quicker spin that way. Then
That's impressive.
that one. Or that's the problem with really fast spin. Okay. What were the other observations you made that made you think that one was different?
There's like all of the mass is kind of closer to the rotation with Keith's.
Right.
Whereas with the other ones, it's like it can get pretty far away.
Okay. Yes, if you were to look at the moment of inertia, for those of you who have ever heard of a moment of inertia, moment of inertia, what you do is you take the mass times its distance from the axis that you're spinning around, and you sum all of those up, add that all up. It has the smallest moment of inertia, because as you say, the mass is all much more closely, much closer to the axis of symmetry. All right. Yeah.
It also seems to have more of a controlled spin.
Okay.
The other ones, they concentrate a lot harder to get it to not fly all over the place.
Okay. So, other things you saw? Yes.
I'm kind of going off of what Rich said, but like those two, they their spin kind of had help because once it gets to like the flat side, it's gonna just like tip over.
Oh, okay.
Like, but when it's like this, it has to be like their force on it, and then on his it was more even, like the whole way.
Okay, thank you. Anything else, anything different that any of you saw? All right. The one we're going to be talking about is actually the one Stephen was talking about. If I do it along the long axis, I can get nice, stable spin. I can make it spin so that it only spins along the long axis. It doesn't spin around any other axis. And if I take this axis through here, which actually has the largest moment of inertia, I can get it to just spin around that axis and get nice, stable spin around that axis. No matter how good I am, no matter how long I train, no matter how uniform my rectangular solid is, I can never, in this life, get this rotation to be only around the one axis. It will always tumble. If I spin it, you'll notice I always get rotation around another axis. And so I never get stable rotation around that axis. I can get stable rotation around the long axis. I can get stable rotation around this axis, which actually has the largest moment of inertia. I can never get stable rotation around that axis, which is actually the middle moment of inertia. This is the smallest moment of inertia. This is the biggest moment of inertia. This is the one in between. Turns out that the one with the in-between moment of inertia, you can never get stable rotation around that axis. So that's what we're looking at. We're going to be talking about equilibria. And an equilibrium, equilibria is the plural for equilibrium, is just a state of the system that does not change. So around the long axis of the eraser, I can set it spinning, and it sits and just spins around that axis, and it never changes. We just get a nice stable spin, just keeps doing it till friction and other things stop it. But if I were out in space and I just set this thing spinning, it would just sit there and spin potentially for the rest of eternity. Well, that might be a bit much, but don't know exactly what will cause the Earth to receive its paradisiacal glory, but I suspect it will have some disturbance to the local space. So that's an equilibrium spin. You know, that has a nice stable, that doesn't. That has a nice stable equilibrium. This one, same thing, I can get nice stable spin. If I were out in space and started it spinning this way, it would just sit there and spin, spin. Nothing would change. But not this one. I can't get it to spin there. It always changes, always does something a little different, gets off from what I started it doing. So that's what we're going to be interested in, our equilibrium. If we go and let's look at another example of a discrete dynamical system, or the other term for what we've been talking about and using is difference equations. So when we did the flu lab model last time, and we came up with that difference equation that, you know, the number of zombies at time t minus 1 minus the number of zombies at time t was proportional to the number of zombies that you had times the difference between the maximum population and the number of zombies. This thing right here has two names, of one sort of fancier than the other. Fancy one is this is a discrete dynamical system. And the other one is a little more direct. It's a difference equation. Difference equation makes some sense because what we're looking at is the difference between consecutive values of the thing that I'm measuring. And it's an equation, so it's a difference equation. The discrete dynamical system takes a little more. By discrete, discrete means that whatever we're measuring, it changes in chunks. It doesn't change continuously. In some sense, you can't break it down into, you know, as small a pieces as you want to. There's some sort of fundamental unit that you just can't split up. In this case, it would be people. You can't talk about half a person being sick.
Talking about zombies, you can't.
Really? Sorry. You'll have to forgive the fact that I have never watched horror movies with zombies, and so I have no idea of the physics involved. So, but generally speaking, we don't cut people up, and so we don't talk about half a person being sick. So changes in chunks, changes in units. That's the discrete part. Dynamical just means that it is changing. There's something going on, and then system just means that there's more than just one blob sitting there doing nothing. So that's what we'll be looking at, our equilibria of discrete dynamical systems or difference equations. If we go back to this flu example that we were doing last time, are there any values